Welcome to Chapter 8, Flight Instruments. In this chapter, we're going to explore the key instrument systems that pilots rely on to fly safely and accurately, whether in visual or instrument meteorological conditions. We'll cover the pitot-static system and the instruments it powers, including the airspeed indicator, altimeter, and vertical speed indicator. We'll then move into the vacuum system and the gyroscopic instruments it drives, such as the attitude indicator and heading indicator. Finally, we'll examine the magnetic compass, one of the oldest and most fundamental navigation tools in aviation. Understanding how these instruments work, what can cause them to fail, and how to recognize errors or malfunctions is essential knowledge for every pilot. Let's get started. To safely operate any aircraft, a pilot must have a solid understanding of the flight instruments, not just how to read them, but how they work, what can go wrong, and how to recognize when something isn't right. In this chapter, we'll cover four main areas. We'll start with the pitot-static system, which provides the pressure inputs that drive several key instruments. From there, we'll look at those instruments directly: the airspeed indicator, altimeter, and vertical speed indicator, along with the errors and limitations associated with each. Next, we'll examine the vacuum system, which serves as the power source for the gyroscopic instruments. Speaking of which, we'll then cover those gyroscopic instruments themselves, the turn coordinator, attitude indicator, and heading indicator, and how they function. Finally, we'll wrap up with the magnetic compass, one of the oldest and most reliable navigation tools in aviation, including the errors it's subject to and how pilots correct for them. By the end of this chapter, you'll have the foundational knowledge needed to interpret your instruments accurately and respond appropriately when something doesn't behave as expected. The pitot-static system is one of the most fundamental systems on any aircraft, providing the pressure data needed to operate three critical flight instruments. The system works by measuring two types of air pressure. Static pressure is the ambient atmospheric pressure surrounding the aircraft, while dynamic pressure, also called ram air pressure, is generated by the aircraft's forward motion through the air. The pitot tube captures both of these pressures together, while dedicated static ports measure static pressure alone. These inputs are then fed to three instruments. The airspeed indicator, or ASI, compares dynamic and static pressure to calculate how fast the aircraft is moving through the air. The altimeter uses static pressure to determine the aircraft's altitude above a reference point. And the vertical speed indicator, commonly called the VSI, measures the rate of change in static pressure to show whether the aircraft is climbing, descending, or in level flight. Understanding how this system works and recognizing when it may not be working correctly is essential for safe flight operations. Any blockage or malfunction in the pitot-static system can directly affect the accuracy of all three instruments simultaneously. The pitot tube is the primary source of impact pressure for your pitot-static system. Its job is to capture total pressure, which is the combination of dynamic pressure and static pressure. Of those two components, it's the dynamic pressure, the pressure created by the aircraft moving through the air, that actually drives the airspeed indicator. In fact, the ASI is the only instrument in the system that uses pitot pressure directly. Understanding the physical design of the pitot tube helps you recognize potential failure points. The small opening at the front admits total pressure into the system, while a drain hole at the rear expels any moisture that enters the tube. Both of these openings must be checked during your pre-flight inspection. A blocked drain hole can trap water, and a blocked inlet will cause an immediate loss of airspeed indication. Pitot tube covers are your best defense against insect nesting, which is one of the most common causes of blockage. Always remove the cover before flight and inspect the opening carefully. One additional point worth noting: wind striking the aircraft at less than 90 degrees off the nose will still register on the airspeed indicator. This is important to keep in mind during ground operations on a windy day, where you may see ASI movement even while the aircraft is stationary. The static pressure chamber is a critical part of the pitot-static system. It vents to free, undisturbed air on the side of the aircraft and supplies static pressure to all three of your pitot-static instruments: the airspeed indicator, the altimeter, and the vertical speed indicator. If that primary port becomes blocked by ice, debris, or moisture, you have a backup option, the alternate static source located inside the flight deck. However, using the alternate source introduces errors you need to understand. Because flight deck pressure is slightly lower than outside atmospheric pressure, your altimeter will read higher than your actual altitude. Your airspeed indicator will show faster than your true airspeed, and your vertical speed indicator will momentarily indicate a climb before settling. These are not failures. They are predictable, known errors. Always consult your aircraft flight manual or pilot's operating handbook for the specific correction values applicable to your aircraft. As a last resort, if no alternate static source is available, breaking the glass face of the vertical speed indicator will introduce cabin air into the static system. Be aware this renders the VSI completely inoperative, but it restores function to your altimeter and airspeed indicator. Know this procedure before you need it. The altimeter is one of the most critical instruments in the cockpit, and understanding how it works is essential for safe flight operations. At its core, the altimeter uses a stack of aneroid wafers, thin, sealed capsules that were evacuated and sealed at the standard sea level pressure of 29.92 inches of mercury. As the aircraft climbs and static pressure decreases, these wafers expand. As the aircraft descends and pressure increases, they compress. This mechanical movement is translated through a series of linkages to drive 3 pointers on the instrument face. The long, thin needle indicates hundreds of feet, the short, wide needle indicates thousands of feet, and the long needle marked with a triangle indicates tens of thousands of feet. Now here is the critical concept to understand. The altimeter only reads true altitude under very specific conditions. Those conditions are standard sea level pressure of 29.92 inches of mercury, a standard temperature of plus 15 degrees Celsius, and both pressure and temperature decreasing at standard rates as altitude increases. In the real world, these conditions rarely exist perfectly, which is why understanding altimeter errors and proper setting procedures is so important. We will explore those implications as we continue. 2 critical axioms govern how non-standard pressure and temperature affect your altimeter, and both carry the same warning. You may be lower than you think. Starting with pressure. When you fly from a high-pressure area into a low-pressure area without updating your altimeter setting, the instrument will read higher than your actual altitude. The axiom, going from high to low, look out below, is your memory anchor. The altimeter doesn't know the pressure has changed, it only knows what you've told it. This is why obtaining current altimeter settings from weather stations and ATC along your route is so important. The same risk applies with temperature. Cold air is denser than standard, which means the air column is compressed. Your true altitude will be lower than what the altimeter indicates. Memorize from hot to cold, look out below. This effect becomes especially dangerous in mountainous terrain, where obstacle clearance margins are already tight. When operating in cold temperatures, you should fly at a higher indicated altitude than the published minimum to ensure you maintain adequate separation from terrain and obstacles. Both of these axioms are not just memory devices, they are life-saving principles you must apply every flight. The altimeter is one of the most critical instruments in the cockpit, and knowing how to set it correctly is essential for safe flight operations. To set the altimeter, dial the current altimeter setting into the Colesman window. This value represents station pressure that has been mathematically reduced to sea level. You should update this setting regularly throughout your flight by monitoring ATC, ATIS, AWIS, or ASOS broadcasts. Keep in mind that a difference of just 1/4 inch of mercury translates to approximately 250 feet of altitude error. An error that could have serious consequences, especially in mountainous terrain or during instrument approaches. Before departure, always verify your altimeter accuracy by checking that it reads within 75 feet of the surveyed field elevation after inputting the current setting. If it falls outside that range, the instrument should be considered unreliable. There are 5 types of altitude every pilot must understand. Indicated altitude is simply what you read directly off the instrument. True altitude is your actual height above mean sea level. Absolute altitude is your height above the terrain directly below you, expressed as AGL. Pressure altitude is what the altimeter reads when set to the standard datum of 29.92 inches of mercury, and this is used for performance calculations and flight levels. Finally, density altitude is pressure altitude corrected for non-standard temperature, and it is density altitude that directly governs your aircraft's performance, particularly critical on hot, high-elevation days. The vertical speed indicator, or VSI, is a differential pressure instrument that uses static pressure to indicate your rate of climb or descent in feet per minute. Understanding how it works internally helps you use it more effectively in the cockpit. Inside the instrument, static pressure is routed directly into a diaphragm, while the outer case receives that same static pressure but through a calibrated restricted leak. When the aircraft climbs or descends, the pressure inside the diaphragm changes immediately, but the case pressure lags behind due to that restriction. This pressure differential causes the needle to deflect, indicating vertical movement. The VSI gives you two distinct types of information. The first is trend. The needle responds almost immediately to show you the direction of vertical movement, either up or down. The second is rate, the actual feet per minute value, which only becomes reliable after the instrument stabilizes, typically after a 6 to 9 second lag. This means you should not chase the needle during initial pitch changes. The instantaneous VSI, or IVSI, addresses this lag by incorporating accelerometers that detect vertical movement immediately, giving you accurate rate information without waiting for pressure to stabilize. This makes the IVSI particularly valuable during instrument approaches and in high workload environments where precise vertical rate awareness is critical. The airspeed indicator measures the dynamic pressure difference between the pitot tube and static port, giving us the various forms of airspeed we use in aviation. Let's walk through each one. Indicated airspeed, or IAS, is the raw reading directly off the instrument. This is the value you'll find referenced throughout the airplane flight manual and pilot's operating handbook for performance data such as rotation speeds, flap limits, and maneuvering speed. It's your primary in-cockpit reference. Calibrated airspeed, or CAS, takes that indicated reading and corrects it for any installation error in the pitot-static system and minor instrument error. At most cruise speeds, these corrections are small, but they become more significant at slower airspeeds or high angles of attack. True airspeed, or TAS, goes one step further by correcting TAS for altitude and non-standard temperature. As you climb into thinner air, TAS increases above KS for the same indicated reading. TAS is what you'll use when filing a flight plan and estimating en route times. Finally, ground speed is your actual speed across the surface. It's simply TAS adjusted for the wind component. Add a tailwind, subtract a headwind. Ground speed is critical for fuel planning and arrival time calculations, but it is not a value displayed on the airspeed indicator itself. The airspeed indicator uses a system of color-coded arcs and lines to give you immediate visual reference for safe operating speeds. No mental math required. The white arc spans from VS0 to VFE. VS0 is your stall speed in the landing configuration, and VFE is your maximum flap extension speed. Anytime you're operating with flaps deployed, you need to be within this arc. The green arc is your normal operating range, running from VS1, stall speed in a clean configuration, up to VNO, the maximum structural cruising speed. This is where you'll spend most of your flight time, and it's safe to operate here in all conditions. The yellow arc from VNO to VNE is the caution range. You may enter this range only in smooth air, and even then, you should do so with care. Turbulence in this range can place excessive stress on the airframe. The red line marks VNE, the never exceed speed. Operating at or beyond this speed risks structural damage or failure. Treat it as an absolute limit with no exceptions. Understanding these markings and what they represent is fundamental to safe airspeed management throughout every phase of flight. Beyond the color-coded arcs and markings printed directly on the airspeed indicator face, there are several critical airspeed limitations you must know that do not appear on the instrument itself. These speeds are found in the pilot's operating handbook and must be committed to memory. Maneuvering speed, or VA, is the maximum speed at which you can apply full deflection of a single flight control without risking structural damage. Importantly, VA varies with aircraft weight. A lighter aircraft has a lower maneuvering speed, so always verify the correct value for your current weight. For aircraft with retractable landing gear, VLO is the maximum speed for operating the gear, meaning extending or retracting it, while VLE is the maximum speed for flight with the gear already extended. These are often different values, so know both. Vx and Vy represent best angle of climb and best rate of climb speeds respectively. These are essential for obstacle clearance and efficient climb performance. Finally, for multi-engine pilots, VYSE is the single-engine best rate of climb speed, marked as the blue line on the airspeed indicator, and VMC is the minimum control speed with one engine inoperative. These speeds are critical for safely managing an engine-out emergency in a twin-engine aircraft. Pitot-static blockage is a serious system malfunction that every pilot must be able to recognize and respond to correctly. Let's look at what happens in each scenario. If the pitot tube becomes blocked but the drain hole remains open, ram air pressure is lost while residual pressure drains away, causing the airspeed indicator to drop to 0. However, if both the pitot tube and the drain hole are blocked, ram air pressure becomes trapped. In this case, the airspeed indicator behaves like an altimeter. It responds to changes in static pressure rather than actual airspeed. During a climb, the trapped pressure makes the ASI show increasing speed, and during a descent, it shows decreasing speed. This is a particularly deceptive failure because the instrument continues to respond, just not to what you think it is responding to. A blocked static port presents a different set of problems. The altimeter will freeze at the altitude where the blockage occurred, the vertical speed indicator will read a constant 0, and the airspeed indicator will become inaccurate. In this case, the alternate static source becomes essential. Knowing these failure signatures allows you to quickly identify which part of the system has been compromised and take the appropriate corrective action before the situation becomes dangerous. Modern aircraft increasingly rely on electronic flight displays, commonly referred to as glass cockpit systems, to present critical flight information to the pilot. At the heart of this system is the primary flight display, or PFD, which consolidates what was traditionally known as the six-pack: the airspeed indicator, attitude indicator, altimeter, turn coordinator, heading indicator, and vertical speed indicator, all onto a single liquid crystal display screen. This integration significantly improves reliability by reducing the number of individual mechanical instruments that can fail independently, and it also reduces panel clutter, allowing for a cleaner, more organized cockpit environment. Alongside the PFD, the multifunction display, or MFD, serves a separate but equally important role, presenting navigational maps, engine monitoring data, and other supplementary information. Together, these two displays give the pilot a comprehensive and intuitive picture of both aircraft performance and situational awareness. As you transition to glass cockpit operations, it is important to understand not just where information is displayed, but how these systems are interconnected and what your procedures should be in the event of a display failure. The electronic flight display consolidates what were once several separate analog instruments into a single integrated primary flight display, or PFD. Understanding how each element is presented on that display is essential for scanning and interpreting flight information accurately. Starting on the left side of the PFD, the airspeed tape is a vertical scrolling scale that replaces the traditional round airspeed indicator. It uses color coding to clearly show operating ranges at a glance, and includes reference bugs for VX, VY, and VR. True airspeed is calculated and displayed at the bottom of the tape using data from the air data computer combined with inputs from the outside air temperature probe. The center of the display is dominated by a full-width artificial horizon driven by the attitude and heading reference system, or AHRS. Below it sits an HSI-style heading indicator. You'll also notice that the traditional inclinometer ball has been replaced by a slip and skid bar, which functions the same way but is integrated directly into the display. On the right side, the altimeter tape scrolls in 20-foot increments, and the vertical speed indicator appears as either an arc or a secondary tape adjacent to it. Both include trend indicators to help you anticipate changes before they fully develop. All of this air data flows from the air data computer, a solid-state device that processes pitot and static inputs and feeds both the PFD and the autopilot system. Because it is a discrete, replaceable unit, maintenance teams can swap it out quickly to reduce aircraft downtime. Trend vectors are a powerful feature of modern electronic flight displays that give you a look-ahead capability for managing your aircraft's energy state. The air data computer continuously calculates the rate of change for both airspeed and altitude, then projects that information forward 6 seconds and displays it directly on the airspeed indicator and altimeter tapes as magenta lines. What this means practically is that the magenta trend vector tells you not just where your airspeed or altitude is right now, but where it will be in 6 seconds if the current rate of change continues. On the airspeed tape, the vector extends upward if you're accelerating and downward if you're decelerating. On the altimeter tape, it works the same way, extending in the direction your altitude is trending. This gives you an early warning system built right into your primary instruments. Rather than waiting to see your airspeed or altitude actually change and then reacting, you can anticipate the change and make smaller, more precise control inputs to stay on target. This is especially valuable during approach, climb, or any phase of flight where tight energy management is critical. Learn to scan these vectors as part of your normal instrument cross-check, and you'll fly more smoothly and precisely as a result. Gyroscopic instruments rely on two fundamental principles that make them incredibly useful for flight: rigidity in space and precession. Rigidity in space means that a spinning gyroscope will maintain its orientation in space, regardless of how the surrounding structure is moved or tilted. Think of it like a spinning top that resists being knocked over. The faster the gyro spins, the greater that rigidity becomes. This property is what makes attitude indicators and heading indicators work. The gyro holds its fixed reference point in space, while the aircraft moves around it. The second principle is precession. When you apply a deflective force to a spinning gyro, the gyro doesn't respond at the point where the force is applied. Instead, it reacts at a point 90 degrees later in the direction of rotation. The rate at which this precession occurs is directly proportional to how much force is applied, and inversely proportional to rotor speed. This behavior is what turn indicators take advantage of. As the aircraft yaws, precession produces a measurable response that indicates the rate of turn. Understanding these two principles gives you a solid foundation for interpreting what your gyroscopic instruments are telling you during flight. Most gyroscopic flight instruments in general aviation aircraft are powered by a vacuum system, and understanding how that system works is essential for safe flight operations. An engine-driven vacuum pump draws outside air through a filtered inlet, directing that airflow across the rotor vanes of the attitude indicator and heading indicator. This spinning action is what keeps the gyroscopes erect and responsive. After passing through the instruments, the air flows through a relief valve, which regulates system pressure and is then vented overboard. The normal operating range for this system is 4.5 to 5.5 inches of mercury, and you should check the suction gauge regularly during flight, not just during your initial scan. If vacuum pressure drops below that range, the gyros will begin to slow down and precess, giving you unreliable instrument readings, a situation that can be especially dangerous in instrument meteorological conditions. The failure may be gradual and subtle, so the suction gauge is your early warning. Because of this vulnerability, most aircraft include an electrical backup for at least one gyroscopic instrument, typically the attitude indicator. Know which instruments in your aircraft are vacuum-driven and which are electrically powered so that in the event of a system failure, you immediately understand which indications to trust. There are two types of turn indicators you need to understand, and while they look similar, they work differently. The turn and slip indicator uses a gyro mounted in the vertical plane and shows only the rate of turn in degrees per second, indicated by a needle. The turn coordinator, on the other hand, has its gyro canted at an angle, which allows it to sense both roll rate and turn rate. This is why the miniature aircraft in a turn coordinator first responds to the roll into the turn, then stabilizes to indicate the actual turn rate. In both instruments, aligning the miniature aircraft wing or needle with the turn index gives you a standard rate turn of 3 degrees per second, which will complete a full 360-degree turn in exactly 2 minutes. Below the gyroscopic display sits the inclinometer, which is simply a ball in a curved fluid-filled tube. This tells you whether the turn is coordinated. If the ball falls inside the turn, you have a slip. Add rudder toward the ball to correct. If the ball falls outside the turn, you have a skid. Reduce rudder pressure. The phrase to remember is step on the ball, meaning apply rudder pressure in the direction the ball has moved to bring it back to center. The turn coordinator gives you 2 critical pieces of information: the rate of turn and whether that turn is coordinated. The inclinometer, that small ball in the curved tube at the bottom of the instrument, tells you immediately whether you are slipping, skidding, or flying in coordinated flight. In a slipping turn, the ball falls to the inside of the turn. This means you have applied too little rudder for the amount of bank. You need more rudder input to bring the ball back to center. In a skidding turn, the ball swings to the outside. Here you have applied too much rudder, and you need to reduce rudder pressure to correct it. The memory aid is simple and effective. Step on the ball. Whatever side the ball has moved to, apply rudder pressure on that same side, and it will return to center. Coordinated flight means the ball is centered, the aircraft is neither slipping nor skidding, and all aerodynamic forces are properly balanced. This is your normal, efficient state of flight. Some aircraft also use a yaw string, a simple piece of yarn or string attached to the windscreen centerline. If it deflects left or right, you are out of coordination. It is a low-tech but highly reliable backup to your inclinometer. The attitude indicator is one of the most essential gyroscopic instruments in the cockpit, giving you an immediate and reliable picture of the aircraft's orientation relative to the horizon. At its core, the attitude indicator uses a gyro mounted in the horizontal plane. Because of the gyroscope's rigidity in space, the internal horizon bar remains fixed while the aircraft moves around it. This means that as you pitch up, pitch down, or bank left and right, the gyro stays aligned with the Earth's horizon, and the instrument reflects those changes instantly. There is no lag, making it your primary reference for aircraft attitude during instrument flight. When reading the instrument, always focus on the relationship between the miniature aircraft symbol and the horizon bar. Do not rely solely on the bank angle scale for determining the direction of bank. The miniature aircraft-to-horizon relationship gives you the clearest and most accurate picture of what the aircraft is actually doing. Be aware of the instrument's physical limits. Bank indications are reliable up to approximately 100 to 110 degrees, and pitch indications up to about 60 to 70 degrees. If the aircraft exceeds these limits, the gyro can tumble, meaning it loses its reference orientation and begins displaying completely erroneous information. After a tumble, the instrument must be allowed to re-erect before it can be trusted again. Always cross-check your other instruments to catch this situation early. The attitude indicator is often considered the most important instrument in the panel, and for good reason. Unlike other flight instruments that infer aircraft attitude from pressure changes or gyroscopic precession effects, the attitude indicator gives you a direct, visual representation of exactly what your aircraft is doing in 3-dimensional space. Every combination of pitch and bank, whether you're in a shallow coordinated turn, a steep climbing bank, or an unusual attitude, is accurately displayed in real time. The relationship between the miniature aircraft and the horizon bar is intentionally intuitive. Whatever you see on that instrument mirrors precisely what your real aircraft is doing relative to the actual horizon outside. This one-to-one correspondence makes it far easier to interpret under stress or in reduced visibility conditions. When transitioning to instrument flight, pilots are taught to cross-check all instruments, but the attitude indicator serves as the primary reference point around which that scan is built. Trusting it, understanding it, and keeping it centered in your instrument scan are foundational skills for any pilot operating in instrument meteorological conditions. The heading indicator is a gyroscopic flight instrument that provides a stable, reliable directional reference, free from the errors that affect a magnetic compass. Unlike the magnetic compass, which suffers from turning and acceleration errors, the heading indicator gives the pilot a steady heading readout during all phases of flight. Inside the instrument, the rotor spins in a vertical plane. The compass card is fixed to the gyro rotor assembly, which remains rigid in space due to gyroscopic inertia. As the aircraft turns, the airframe rotates around that rigid gyro, and the compass card reflects that change in heading. However, heading indicators do have known error sources you need to understand. Bearing friction causes precession drift over time, and the rotation of the Earth itself can introduce up to 15 degrees of error per hour. For this reason, free gyro heading indicators must be cross-checked and reset against the magnetic compass approximately every 15 minutes during flight. More advanced horizontal situation indicator models, or HSIs, incorporate a magnetometer that continuously slaves the gyro to magnetic north automatically, eliminating the need for manual resetting. One final limitation to keep in mind: if the aircraft exceeds approximately 55 degrees of pitch or bank, the gyro can tumble, causing the instrument to become unreliable until it re-erects. Always be aware of this boundary during unusual attitude recoveries. Modern glass cockpit aircraft replace traditional mechanical gyroscopes with an attitude and heading reference system, commonly known as AHRS. Instead of free-spinning gyros that are vulnerable to tumbling and gimbal lock, AHRS uses solid-state laser technology to continuously sense aircraft movement. This means the system remains accurate and reliable at any pitch or bank attitude with no mechanical limitations. The AHRS sends pitch, bank, and heading information directly to the primary flight display. Heading information specifically comes from an internal magnetometer, which senses the Earth's magnetic flux lines to determine direction. Working alongside the AHRS is the flux gate, sometimes called a flux valve. This device consists of a segmented soft iron ring fitted with 3 pickup coils. An excitation coil energized at 400 Hz alternately saturates and releases the iron frame. As this happens, Earth's magnetic flux is alternately blocked and allowed to flow, inducing a current in each of the 3 pickup coils. The pattern of that induced current changes depending on which direction the aircraft is pointing. This changing current pattern is then transmitted through a synchro system to drive the compass card on the HSI or RMI. Together, the AHRS and FluxGate provide highly accurate, reliable attitude and directional information to the flight crew. The Angle of Attack Indicator, or AOA indicator, is a critical tool for understanding your stall margin at any given moment during flight. Rather than relying solely on airspeed, the AOA indicator shows you the margin between your current angle of attack and the critical angle of attack, the point at which the wing will stall. Here is a fundamental principle you must internalize. An aircraft will always stall at the same critical angle of attack, regardless of weight, bank angle, temperature, density altitude, or center of gravity position. This means airspeed alone is not a reliable stall indicator, because the airspeed at which a stall occurs can change significantly based on these variables. The AOA indicator removes that ambiguity. It gives you a direct, visual representation of the aircraft's energy state, essentially the balance between airspeed, altitude, drag, and thrust at any point in time. Whether you are flying a steep turn, carrying extra weight, or operating in high-density altitude conditions, the AOA indicator tells you exactly how close you are to the aerodynamic limit of the wing. Understanding and using this instrument effectively is a cornerstone of modern stall awareness and overall flight safety. The magnetic compass is one of the oldest and most fundamental navigation instruments in aviation, and it remains a regulatory requirement under 14 CFR Part 91 for both VFR and IFR flight. Despite advances in modern avionics, the magnetic compass serves as a critical backup and is always part of the required equipment list. In terms of construction, the compass consists of 2 small magnets attached to a float, sealed inside a housing filled with compass fluid. That fluid dampens the movement of the card and reduces vibration. The graduated compass card is read through a glass window, and a fixed lubber line marked on the housing serves as your reference for reading the heading. The pivot mechanism allows the compass to remain functional during normal maneuvering, tolerating bank angles of up to approximately 18 degrees. However, once you exceed that, the compass indications become unreliable and erratic. This limitation is important to understand, especially during steep turns or unusual attitudes. Because of its simple, self-contained design with no dependence on electrical power, the magnetic compass will continue to function even during total electrical failure, which is precisely why it remains a required instrument and a cornerstone of aircraft navigation. The magnetic compass, while simple and reliable, is subject to two important errors that pilots must understand and account for: variation and deviation. Variation is the angular difference between true north and magnetic north. This occurs because the magnetic North Pole is not in the same location as the geographic North Pole. Variation is depicted on aeronautical charts as isogonic lines, lines connecting points of equal variation. The agonic line, which passes near Chicago, is where variation is 0. East of the agonic line, variation is easterly, meaning you add it when converting from magnetic to true. West of the agonic line, variation is westerly, and you subtract it. Importantly, variation has nothing to do with the aircraft itself. It is a fixed geographic phenomenon that does not change with your heading. Deviation, on the other hand, is caused by the aircraft's own magnetic influences, things like electrical currents, magnetized metal components, and avionics. Unlike variation, deviation changes as the aircraft changes heading. Aviation maintenance technicians minimize deviation by performing a process called swinging the compass, physically repositioning small compensating magnets within the compass housing. However, some residual error nearly always remains. That remaining error is recorded on a compass correction card, which is mounted in the cockpit near the compass for the pilot to reference during flight. When navigating with a magnetic compass, you need to account for two separate correction factors before you can trust the heading you fly. The first is variation, which is the angular difference between true north and magnetic north. The second is deviation, which is the error introduced by the aircraft's own magnetic fields affecting the compass. To work from a true course down to a compass course, follow this sequence. Start with your true course and apply variation to get your magnetic course. Then apply deviation to arrive at your final compass course, the heading you actually fly. In our example, we begin with a true course of 180 degrees. With 10 degrees of west variation, we add, because west variation is added, giving us a magnetic course of 190 degrees. We then subtract 2 degrees of east deviation, arriving at a compass course of 188 degrees. A helpful memory aid is the phrase, fly compass, magnetic plus or minus deviation, true plus or minus variation, working from the bottom up when converting, or top down when planning. Just as a small pressure difference of a quarter inch of mercury can produce 250 feet of altitude error, even a single degree of uncorrected compass error accumulates over distance. Precise correction at every step is essential to maintaining safe and accurate navigation. When turning through north, the magnetic compass will actually lead the turn, meaning it moves ahead of the aircraft's actual heading. Because of this, you need to stop the turn early. The rule of thumb is to roll out 15 degrees plus half your latitude before reaching your desired heading. For example, if you are at 40 degrees north latitude and turning to north, you would stop the turn when the compass reads 35 degrees, which accounts for the 15-degree base plus 20 degrees, half of 40. When turning through south, the opposite effect occurs. The compass lags behind the actual heading, meaning it falls behind where the aircraft is truly pointing. To compensate, you must allow the compass to pass through your desired heading before rolling out. Again, apply the same formula, 15 degrees plus half the latitude, but this time beyond the desired heading. Both of these errors are caused by the vertical component of the Earth's magnetic field acting on the compass card during banked turns. Understanding and applying these corrections is essential for accurate compass navigation, particularly when operating without a functioning heading indicator. Two additional errors pilots must understand are acceleration error and oscillation error. Acceleration error occurs specifically on easterly and westerly headings. When you accelerate on these headings, the compass will falsely indicate a turn toward north. When you decelerate, it will falsely indicate a turn toward south. A simple memory aid to remember this is A and S, acceleration north, deceleration south. This error does not occur on northerly or southerly headings, only when you are tracking east or west. Oscillation error is essentially a combination of all the various compass errors working together, causing the compass card to swing back and forth rather than settle on a steady indication. Because of this swinging motion, you should never attempt to set your heading indicator to a single momentary compass reading. Instead, observe the compass through several complete swings and use the average value between those swings. This gives you a far more accurate and reliable reference heading. Both of these errors reinforce why the magnetic compass, while essential as a backup instrument, requires careful interpretation and cross-checking with other navigation instruments during flight. The vertical card compass is an improvement over the traditional compass design. Instead of a floating card that can be difficult to read, the vertical card compass displays heading information in a format similar to a heading indicator, making it much easier to interpret at a glance. It also uses eddy current damping to reduce the oscillation that makes standard magnetic compasses so difficult to read in turbulence or during maneuvers. The remote indicating compass, commonly integrated into the horizontal situation indicator or HSI, takes compass technology a step further. It combines a flux valve, which is typically mounted in the wingtip to isolate it from the aircraft's own magnetic interference, with a gyroscope-stabilized compass card. This gives you the accuracy of magnetic sensing combined with the stability of gyroscopic rigidity. The system operates in two modes. In slaved gyro mode, the system automatically corrects itself to align with magnetic north using input from the flux valve. In free gyro mode, the pilot manually adjusts the heading card as needed. When the remote magnetic indicator, or RMI, is incorporated, it adds ADF and VOR bearing pointers directly onto the compass card, giving the pilot an integrated navigation picture all in one instrument. This significantly reduces cockpit workload during instrument flight. The outside air temperature gauge, or OAT gauge, is a straightforward but essential instrument in the cockpit. It operates on a bimetallic helix principle, meaning it uses two metals bonded together that expand and contract at different rates as temperature changes. This mechanical reaction causes the sensing element to twist or untwist, moving the needle across the dial. The sensing probe is mounted externally on the aircraft so it is directly exposed to the airstream, giving you a real-time reading of the air temperature surrounding the aircraft. Most OAT gauges are calibrated in both Celsius and Fahrenheit, making them versatile across different operating environments and international airspace. The practical value of this instrument goes well beyond simple temperature awareness. You will use OAT readings when computing true airspeed, since air density directly affects how fast you are actually moving through the air mass. It also helps you assess the temperature lapse rate as you climb, supports density-altitude calculations, and is critical for recognizing icing conditions. When the OAT is hovering near 0 degrees Celsius in visible moisture, you need to know that immediately. Understanding how to read and apply your OAT gauge accurately is a fundamental part of sound aeronautical decision-making. Before departure, you must verify that each of your six-pack instruments is functioning correctly. Let's walk through the key checks. On the altimeter, set the current altimeter setting and confirm the indicated altitude is within 75 feet of the known field elevation. The VSI should read at or very near 0. If it shows a slight offset, note that value as your 0 reference in flight. The airspeed indicator should read 0 on the ground, or slightly above 0 if there's a strong headwind, and you should confirm it rises during the takeoff roll. The turn coordinator should reflect correct turn direction while taxiing, and the inclinometer ball should swing opposite the direction of the turn. As the attitude indicator's gyro spools up, listen for any abnormal sounds and wait for the horizon bar to stabilize before flight. Finally, the heading indicator should also spool up quietly, indicate correct turn direction during taxi, and be set to match your magnetic compass before takeoff. The inclinometer should be full of fluid with no air bubbles visible and the ball resting at the lowest point. These checks take only moments but are critical for catching instrument faults before you ever leave the ground. Let's bring together the key concepts from this section on flight instruments. The pitot-static system powers your airspeed indicator, altimeter, and vertical speed indicator. If either the pitot or static port becomes blocked, you will see instrument errors. Know the symptoms for each scenario and remember that your alternate static source is available when needed. For the altimeter, always set the current altimeter setting before flight and update it throughout. Remember the phrase, high to low, look out below. When flying from high pressure to low pressure or from warm air to cold air, your actual altitude will be lower than indicated. For gyroscopic instruments, understand that rigidity in space keeps the gyro stable, while precession causes it to respond to applied forces. Monitor your vacuum gauge and cross-check instruments regularly to catch any gyro degradation early. Finally, the magnetic compass is reliable but subject to multiple errors: variation, deviation, dip, and acceleration and oscillation errors. Always apply corrections in the proper sequence from true to magnetic to compass heading, and reset your heading indicator against the compass approximately every 15 minutes. These fundamentals form the foundation of safe and accurate instrument interpretation. Let's take a moment to bring together everything covered in this chapter. The pitot-static system powers three key instruments. The airspeed indicator uses both pitot and static pressure, while the altimeter and vertical speed indicator rely on static pressure alone. Understanding blockage symptoms for each is essential, because a failed or blocked source can give you dangerously misleading information in flight. When it comes to the altimeter, make sure you're comfortable with all 5 types of altitude and know when to use each one. Setting the Colesman window correctly keeps you accurate. And remember that density altitude is your go-to concept when assessing aircraft performance. For gyroscopic instruments, the 2 fundamental principles are rigidity in space and precession. Vacuum-driven systems require between 4.5 and 5.5 inches of mercury to operate reliably. Modern aircraft increasingly use AHRS technology, which replaces traditional spinning gyros with solid-state sensors. Finally, the magnetic compass requires you to account for both variation and deviation. Remember the ANDS rule for acceleration errors, and keep in mind that northerly headings lead and southerly headings lag during turns. The closing thought here is the most important one. Knowing how each instrument works and recognizing when something isn't right is what allows you to use your instrument safely and confidently in any situation.